Distinguished colleagues and guests, good afternoon. It's February 26th, 2 p.m. Moscow time, and we're beginning the panel session for the defense of the thesis by Demidova. The thesis is submitted for the academic degree of the candidate of sciences in physics and mathematics. The specialization is 010204, mechanics of hard body under deformation. The topic of the thesis is the effects of unelastic strain recovery during the martensite transformations under isothermal conditions. Under the order issued by the academic secretary of St. Petersburg State University, Alexander Gnotov, as of December 7th, 2020, I, Svetlana Bauer, Doctor of Sciences in Physics and Mathematics, Professor of the Department of Theoretical and Applied Mechanics of St. Petersburg State University, was appointed the chairperson of this dissertation board, and the order also approved the candidacies of the members of our board. Let me introduce them. Yulia Pronina, Doctor of Sciences in Physics and Mathematics, Associate Professor, Professor of the Department of Computational Methods of Deformable Body and Mechanics, St. Petersburg State University. Viktor Morozov, Doctor of Sciences, Associate Professor, Professor of the Department of Physical Mechanics of St. Petersburg State University, and the following members of the board are working remotely today: Tatiana Arlova, Doctor of Sciences and Senior Researcher of the Laboratory Physics of Profiled Crystals of the Solid State Physics Department of the Physics and Technology Institute of the Russian Academy of Sciences. Do you hear us and see us, Tatiana? Yes, I do. And Vasily Rybanyk, Doctor of Technical Sciences, Director of the Institute of Technical Acoustics of the National Academy of Sciences of Belarus. Do you hear us and see us? Yes, I do. And our candidate for the degree, Elena Demidova, and Natalia Resnina, Doctor of Sciences in Physics and Mathematics, Professor of the Department of General Mathematics and Informatics, St. Petersburg University, is the thesis supervisor. And dear colleagues, in order to improve the quality of our connection, kindly turn off your mobile phones and microphones, but don't forget to turn your microphones on when I give you the floor. I would also like to inform you that the panel session of the dissertation board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted from Russian into English and from English into Russian if there is such a need. Currently, we have an email address posted on the page with live broadcast of the board session, and all the listeners can submit their questions to Ms. Demidova online. The thesis regarding the questions regarding the thesis or scientific discussion. So the questions must be related to the presentation or to the content of the thesis. These questions will be forwarded to me by our technical service, and I'll read them out during the discussion. And they should be related to the speech of our candidate for the degree, and don't forget to give your name and position if you submit a question. The questions that have nothing to do with a scientific discussion or dissertation, text will not be voiced. Under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by local normative acts, the session of the dissertation board is valid, providing 2/3 of the appointed board members are present. Our dissertation board consists of 5 people. Everyone is with us today, including 2 members of the board who are working remotely today. We have a multimedia connection with all the members of the board as well as with our candidate for the degree. Therefore, we have a quorum. Our session should not last more than 2 hours, and the agenda is as follows. First comes the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements, chairman's replies to questions, if any, then candidate's presentation providing an overview and findings of the research, 15 minutes for that, and questions to the candidate regarding the presentation, candidate's replies to the questions, 10 minutes for all. Reports of the thesis. On the thesis, the board members will be taking the floor in turns to provide their reviews and questions. 10 minutes per speaker. Then the chairman's report on the thesis. Then the candidate's comments about the reports on the thesis, replies to questions, 20 minutes for that, and then open discussion. Everyone willing to speak out may state their positions or ask questions. Everyone willing to speak out, don't forget to register in the registry form and don't forget to introduce yourself before you are giving the floor. Then the chairman will ask questions submitted during the broadcast via our website. Then the candidates' replies to the questions. Then the presentation of candidates' thesis supervised. Then 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. The discussion of the results of the defense is not broadcast. And next comes open balloting, vote counting, and recording of the results in the protocol, making a decision on whether to confer the academic degree or not, and the candidate's closing speech. Distinguished colleagues, any questions or comments on our agenda? As there are no questions, let us proceed. But before I do that, I kindly ask you to switch off the sound on your mobile phones. Yes, don't forget that. So let me start. The thesis by Elena Demidova for the academic degree of Candidate of Sciences in Physics and Mathematics, the specialization 010204, Mechanics of Hard Body Under Deformation, is titled Effects of Unelastic Strain Recovery During the Martensite Transformations Under Isothermal Conditions. The thesis was approved for the defense by the order of the academic secretary as of November 30th, 2020, and you see that Elena Demidova has prepared her thesis based at St. Petersburg State University, and Natalia Resnina, Doctor of Sciences in Physics and Mathematics, Professor of the Department of General Mathematics and Informatics of St. Petersburg State University, is the thesis supervisor. The list of 13 published works describe the research findings. They include no papers published in peer-reviewed journals recommended by the Ministry of Education and Science, and 3 papers in publications indexed in Web of Science and Scopus. The candidate has submitted the full set of documents to the academic secretary, and the above-mentioned documents comply with item 12 of section 3 of the order. All the documents provided, as far as I'm informed, comply with the requirements and are found in the certification file. The curator of the defense, member of the department of the dissertation board support, has all the copies. And before I give the floor to our candidate for the degree, I would like to ask if there are any general questions to the candidate for the degree, and is there a need to read out the whole list of documents submitted? No need for that. Okay. Okay, then we give the floor to Elena for a short presentation. So, Elena, please, you have 15 minutes. Distinguished members of the board, good afternoon. The title of my dissertation is The Effects of Unelastic Strain Recovery During the Martensite Transformations Under Isothermal Conditions. Starting with 1947, thermoelastic martensite transformations were considered thermal. Starting with 2010, it was demonstrated that in a number of alloys based on titanium and nickel, we can have a martensite phase under permanent temperature that is equal to the temperature of forward transition, regardless of the fact that there are a lot of works on the kinetics of this process. Currently, there are a list of unstudied questions. For example, the impact of holding and temperature on the volume of martensite phase. And also, we don't know whether martensite phase transformation goes along with reverse deformation, and also we don't see the models that can theoretically describe the change of the volumetric shear and isothermal deformation. And along with that, the use of alloys with isothermal martensite transformation would allow us to resolve the problem in the development of actuators working with shape memory. Therefore, the goal was to study martensite transformations and the functional characteristics in isothermal holding of titanium nickel doped with hafnium and copper, and the adaptation of the existing mathematical models to describe these events. As an object of study, we've chosen an alloy, the parameters of which are given on the slide. That's titanium nickel and hafnium. And this choice is explained by the fact that, according to the analysis of literature, isothermal formation of martensite is observed only in materials with high concentration of point defects. And in this alloy, hafnium atoms substitute titanium and copper atoms substitute the sublattice of nickel. Therefore, hafnium and copper are the defects of substitution, and we can expect that in this material we may detect isothermal defects. In order to study the isothermal kinetics, we've chosen the differential scanning, calorimetry, and the method given on the slide. The volumetric shear of the isothermal martensite was calculated according to the formula. E values were defined at different stages of the method. The temperature and the holding time was variable. And on this slide, you see the dependency of the volumetric shear of isothermal martensite, depending on the holding time and on the temperature. And we can see that the volumetric shear of martensite is growing up until the saturation phase, and the value is non-monotonously dependent on the holding temperature, and it reaches peak of 80%. When we see the temperature of forward transition. And it was detected that isothermal kinetics is different for cases when we had holding within the temperature interval and beyond its borders. In order to study the changes of strain during the martensite transformation, we devised the following method. On the initial stage, the sample was cooled down and then heated in the Y temperature interval, and we detected the temperature of these transitions under stress. And certainly this was load applied at all the stages. Then the sample was cooled down up until the holding temperature and was heated, and on the third stage, the sample was cooled down up until the holding time temperature. And after that it was heated. And we see that during isothermal holding, we see a rise of deformation that fully restores during the heating, and it is explained by a reversible mechanism of strain and by the formation of oriented martensite. On this slide, you see the dependency of isothermal deformation on the time of holding. And in all cases, we see that the strain is growing up until a certain parameter, depending on the holding time or strain or temperature. And on this slide, you see the dependency of maximum isothermal strain on the temperature and on the stress. We see that they are not monotonous and they reach peak in cases when stress was performed at the following conditions, and the optimal load was 160 megapascals. And in order to explain, we offered the following mechanism that is based on the fact that the dependency of the volumetric shear of martensite on the temperature for non-defect alloy is different from the similar dependency for the same alloys that have high concentration of point defects, these defect alloys. And this point defect prevents the forward transition, but during the isothermal holding, due to non-zero mobility of atoms, these defects can migrate to neighboring areas, and thus we have the drop of concentration of defects in certain areas, and it will be possible to perform thermodynamic condition of forward transition and martensite phase formation, and the defects will continue to migrate. They can get back to the transformed areas, and their concentration will drop in other areas, and the same process will happen there as well. So thermally activated movement of point defects controls the formation of martensite. And in case when the transition is under specific stress, the temperature of direct transformation moves further, and the volumetric shear of martensite that can be formed in isothermal conditions drops, and the holding temperature moves into the interval. And therefore, the mechanism allows us to describe all the phenomena observed. In order to theoretically describe the kinetics of transformation, we use the Avraami model, according to which we define the dependency of volumetric shear of the new phase from the time of holding. In order to take into account the fact that in the observed alloys, not all the material is able to shift to a new phase during the isothermal holding, we added up a multiplier responsible for maximum volumetric shear of martensite that can be isothermally produced at a certain temperature. And this multiplier, as other parameters, is dependent on temperature, and in our work we defined the equations that describe these dependencies. We used them in the Avraami model and calculated the shear of martensite depending on the holding time, and we see that the experimental data comply with each other. In order to describe the isothermal strain, we use the analytical model devised by Lukashov and Volkov, according to which the material is considered as a combination of grains of different orientation. Each grain can consist of austenite or martensite phase, and martensite can be given in different variants, and the strain is defined as grain strain, and the grain strain was found according to the following formula. The first components are dealing with elastic deformation and temperature expansion, then phase deformation, and microplastic strain connected with the movement of interface boundary. As in our work we didn't see the plastic strain in the model, we calculated it as 0. In order to take to describe the isothermal strain, we added up this formula that characterizes relaxation processes responsible for the defect migration. Above all, we modified the formulas for the evolution of densities of these defects, and as the driver depends on this defect density, and defect density may change in time. During the isothermal holding, we may see the change of the driver of transformation that will lead us to the condition of forward transition and the formation of martensite phase and the growth of phase strain. This modification allowed us to introduce new parameters, and in our work we define the impact of these parameters on the functional characteristics of the materials, and we also define their optimal values. They're given on the table with the constants of materials used during the calculations. And using the microstructural model, we calculated the dependency of isothermal strain on the holding time and maximum isothermal strain on the holding temperature for different kinds of stress. And here you see the dotted line is the theoretical data and full lines are experimental data. And we see that the microstructural model allowed us to describe the phenomena correctly and define the maximum value of isothermal strain, the conditions that allows us to achieve it. I won't read out the conclusions, you can see them in the published version of the presentation, and here are the following provisions for the defense. Dependency of the volumetric shear of martensite on temperature and holding time demonstrate that martensite can emerge in isothermal conditions at temperatures within the forward transformation margin and beyond it at temperatures that exceed the start of transformation temperature. The volumetric shear of martensite is growing in time up until the saturation phase, and the saturation phase is non-monotonously dependent on the holding time and is observed at the temperature of forward transition. The dependencies of deformities observed in isothermal holding of alloy under stress on temperature and time of holding demonstrate that during holding the strain reaches the saturation phase and its volume depends non-monotonely on the temperature of the holding, and the maximum is observed at temperature 6 degrees centigrade, and the dependency on the stress is non-monotonous at 160 megapascals, and the results of calculations of the changes of volumetric shear of martensite and deformity under isothermal holding received with the use of a Rame model and the structural analytical model of Lechachev-Volkov demonstrate that these models can be successfully used to describe the observed phenomena. And I prepared 15 publications. 3 of them are in the Scopus and Web of Science basis, and the results were also tested at 11 international conferences. Thank you very much. Any questions to our candidate? No questions. Okay. And now I will give the floor to the members of the board with their positions, with their reports. We had no external reviews. So all the members of the board submitted their reviews and they were published on the St. Petersburg State University website. Therefore, we can just read out the basic ideas, basic questions. So, please, Yulia, you have the floor. Dear colleagues, hello, I liked the thesis lot because that's actually it is on the margin of science, and that is the phenomenon that which was quite recently discovered, and some specific methodologies were not devised for it by now, and there are no standards for this phenomenon right now. Therefore, our candidate for the degree had to choose new methods of study and also to devise the theoretical substantiation of the observed phenomena. So she offered a brand new theoretical model, and above all, she devised not only the theoretical explanation from the point of view of physics and material science, but she also provided a mathematical model. And I've described everything in detail in my review, therefore I believe that this work fully complies with the requirements to the thesis. It's very interesting, and I had certain questions that I wanted to ask. I'll just shortly read them out. The first question was dealing with the time of saturation of the curve's output. The curve's saturation on MS 3.2. Another question was dealing with the non-monotonic dependence of strain. The maximum is achieved at the same temperature. So that was the second question. And it is 6 degrees lower than the martensite temperature. And next question was the following. It was unclear what is the influence of the change of the concentration of migrating defects to the domains where we didn't have any martensite transformation. And why the maximum share of martensite in the defect alloy still reaches the appropriate share in non-defect alloy, regardless of the fact that in non-untouched domains the share of defects grows. and it's unclear how we should coordinate this numbers between the Avrami model and the model for K coefficient in formula 4.1. Thank you very much for the questions. I'll start with the first one. As for the saturation value, the maximum volumetric share of martensite that I mentioned, that's the value of saturation at a specific temperature. And the thing is that in cases when the isothermal holding was performed within the temperature interval of forward transition, the saturation is achieved quite quickly, less than in 15 minutes. And maybe in my thesis I didn't use the correct wording, but still, for all temperatures, we achieve the saturation phase. And the difference in the values of volumetric shear of isothermal martensite accumulated at 50 or at 5 or 60 minutes were observed when we used higher temperatures than the forward transition temperature. And as for the second question, about the maximum, the isothermal strain is explained by the formation of oriented martensite. So the dependency of all these deformations is directly proportional to the volume of martensite produced, and this volume can be obtained as a difference between the dependencies of the volumetric shear of martensite for non-defect material and for the material with a high concentration of point defects. And the calculation of these dependencies demonstrated that the maximum volumetric share of martensite is accumulated under strain in such conditions when the temperature of holding is 6 degrees lower than the temperature of forward transition and the load equals 160 megapascals. Why these parameters were optimal, it's unclear by now, and in order to get an answer to this question, we need to organize further calculations how this stress influences the general situation. Then the question on the migration of defects and the change of their concentration in different areas. We believe that the defects can migrate to neighboring areas regardless of the transformation, whether it had already happened, and they can get back to the deformed area. And in this transformed area, the concentration of defects grow, and the neighboring area will see a drop, and thus they will have this transformation and martensite formation as well. So the local change of concentration is not stable, but it may drop in time depending on what area is that. And K parameter is multiplied with time n, and we can expect that the size of this parameter should be seconds taken to the order of n. And we can give this parameter in a different mode, and we can express it as certain k1 taken to the degree of n, taken to the order of n, and we'll see a multiplication of k and t, and then it will be taken to the order n. And this new parameter k1 will have the following size, and it will not be dependent on the n parameter, the temperature of holding, and all the sizes will be coordinate, will conform. Thank you very much. I'm fully satisfied with the answer. So no questions. Okay, Victor, please, you have the floor. The first thing that I wanted to mention is that I was lucky to see the development of this topic from the very beginning. And also I would like to say that starting with those workshops held by Professor Likhachov, then on the conference on the plasticity of materials, initially we believe that it is quite exotic to study these alloys, and then these exotics transformed into a very interesting scientific study. As for the development of these studies headed by Vladimir Likhachov. A lot was done during that period of time by his students. Then his students continued this very important study, and now we see that the students of his students continue these studies. And we've heard this wonderful presentation. And as for the thesis itself, Elena graduated from our department, then she joined a PhD course, and we've listened to her results several times, and she always had a very good assessment of the colleagues, and this thesis defense is this final result of her work. I would like to mention the major results that she got. First, she offered the new mechanism responsible for the implementation of the thermoelastic martensite transformation in isothermal conditions, and it was demonstrated that thermoelastic transformation in the alloy happens in isothermal regime due to the controlled kinetics of thermally activated process. Second point, she created a special method to measure the deformation explained by isothermal martensite transformation in order to define its reversal. Then she defined the strain at isothermal holding in the interval of temperatures close to the forward transition temperature, and she also demonstrated that it can be fully reversible as a consequence of martensite transformation. She studied the peculiarities of the changes of the strain, and she demonstrated that the change of strain is observed only in holding at temperatures within the temperature interval, and the strain also depends on the temperature of holding, and its dependency on the strain demonstrates maximum. There was a correct adaptation of the Avrami model that allowed the scientists to describe the change of the martensite shared, also to define the conditions at which there is a maximum formation of martensite. And she also successfully used the martensite, the modernized model of Likhachov-Volkov, and this allowed to describe the changes of strain in the implementation of martensite transformations. And also, in order to vary these parameters, she organized a range of experiments. And I want to mention that I particularly liked the fact that Elena combines experimental study with numerical calculations. These models that she demonstrated reflect those effects that are observed during the experiments. And I would like to dwell upon the following comments that I had. First, in some experimental graphs and in the text of the thesis, you don't give information on the measurement error. Second, in the thesis, all the studies are carried out on one 4-component alloy based on nickel titanium. Therefore, it's unclear how these results can be summarized and used for other alloys based on titanium and nickel, and can it be used for all materials with thermoelastic martensite transformation? And third question, so a phase content and deformation can be dependent on time, and the volumetric share of the phase should be dependent on the speed of change of temperature and the strain speed. Unfortunately, these questions were not covered in the thesis, but it should be mentioned that these are rather recommendations. It's not a reprimand, and it does not these questions do not compromise the value of this thesis. The formal part that I want to read out. The thesis by Demidova, titled "The Effects of Unelastic Strain Recovery During the Martensite Transformations Under Isothermal Conditions," meets the requirements of the orders of September the 1st, 2016, on the procedure of granting academic degrees at St. Petersburg State University. And Ms. Demidova deserves the academic degree of the Candidate of Sciences in Physics and Mathematics and Specialization in Mechanics of Hard Body under deformation. And Article 11 of the above-mentioned order is not violated. Thank you. Thank you very much for the review. So the first question was on the order. When we defined the share of martensite phase, the error was dependent on the basic line on the area of the peak of heat absorption, and it made up 7%. And when we studied electric resistance and strain, we were not interested to measure these values, but we were interested in the change of values. Therefore, we did not assess the error. Therefore, the error is defined by the sensitivity of the equipment, and it made up 1%. Next question was about the data given just for one alloy with 5 atomic copper percent. I continue the study, and I study the isothermal martensite at different holding periods in similar alloys with different content of nickel and copper, and my results demonstrate that there is this a quantitative dependence, and the results are just the same as the ones given in the work. Therefore, that's the general characteristic of this system of alloys. But maximum values of the volumetric shear of isothermal martensite was different for different alloys, and the holding temperature and strain, which allowed us to get maximum deformation, was also dependent on the chemical composition. And in the work, I didn't study the impact of speed of cooling and holding on the volumetric shear of isothermal martensite, but I believe that they will be dependent on the speed of cooling, because at slow change of temperature we will also have the formation of isothermal martensite, due to the fact that we'll see local changes in densities in some areas. Therefore, we'll see martensite there. Did I answer the question? Yes, I'm fully satisfied. Okay. Tatiana, please, you have the floor. Once again, good afternoon. I'll voice my review. I liked the work a lot, and St. Petersburg State University was the organizer of my candidate thesis, and the laboratory that employs the candidate for the degree was also my laboratory. Therefore, I'm glad to be the member of the board. Titanium nickel alloys have been studied for a very long period of time. The interest is growing to them, and it is connected with the discovery of these new martensite transformations. Therefore, the work is quite relevant. It is dedicated to the nature of such transformations, and this work is relevant not just for mechanics of the deformed body, but also for contemporary material science. As for the practical value, it was mentioned as well. So this work can be used in order to develop the actuators, working with shape memory, and the candidate for the degree got a lot of new priority results, and I would like to use this opportunity to mention several of these results. Do you hear me? So she defined the dependencies of the shear of martensite phase on the holding time at different temperatures, and also the conditions on temperature and on holding time. And also she devised the physical model for such isothermal transition. That is a brand new physical model. And also the research demonstrated that martensite transformations under strain go along with strain that can be fully reversible at during heating. And for the first time she used modified models of Avrami and the structural analytical model of Likhachov-Volkov to describe the change of the shear of martensite under load and without it. And the credibility of result is not questioned. First of all, there are methods used that add up to each other, and there are calorimetry methods used here, and all the conclusions and theoretical constructs are conform with contemporary scientific developments, and the work is well structured and was tested at international conferences. And I attended one of the conferences, and I liked the report of our candidate for the degree, and she asked the questions quite brilliantly. There are certain points that I wanted to mention on the work, and let me read them out. Describing the object of the study, this specific alloy, you write that it was initially studied in work number 31, but the results of this work are not described. Therefore, it's unclear whether there was such a contribution of this work. And also, you studied the isothermal transformation by certain indirect methods, with the use of differential scanning, calorimetry, and electric resistance measurement. So it would be interesting to learn the direct structural methods results. Do you have any information on that for such alloys? And also, you say that the substitute defect influences the process of the origin of martensite crystals, and the temperature of the stop of forward transition is not changing for non-defect material, so it's unclear why do you make such a conclusion. And the fourth remark, the study of the strain impact on isothermal transformation was carried out in the expansion regime. So if we replace expansion by compression, what is the result? But still, I would like to mention that these remarks do not compromise the high value of the work. Therefore, I would like to read out the conclusion. The thesis by Elena Demidova, titled Effects of Unelastic Strain Recovery During the Martensite Transformations Under Isothermal Conditions, meets the requirements of the order as of September the 1st, 2016, on the procedure of granting academic degrees at St. Petersburg State University, and Ms. Demidova deserves the academic degree of the candidate of sciences in physics and mathematics and in specialization mechanics of hard body under defamation, and Article 11 of the above-mentioned order is not violated. Thank you very much for the comments. I fully agree with the questions. The question on the work number 31, and the works that previously demonstrated that these alloys may have martensite formation, demonstrated that martensite can be formed in isothermal load at temperatures higher than forward transition temperature, and also these effects can be studied using calorimetry. But the influence of parameters of the holding on the change of the shear of martensite or on the functional characteristics connected with this phenomena, this all was not studied. As for the next question, on the structural study with electron microscopy. Yes, as of today, in 2020, a work was published by a Japanese group, and they studied isothermal formation of martensite using scanning electron microscopy. However, this method allowed us to just prove isothermal formation of martensite. In my future work, I plan to organize similar studies using scanning electron microscopy, and also I plan to study the isothermal formation of martensite under stress using electron microscopy. And as for the change of point effects, the impact on the temperature of the forward transition, this conclusion was based on the fact that, judging by the analysis of literature and my data, all the materials in which we had isothermal formation of martensite were characterized by a very narrow temperature interval of forward transition. If these point effects would influence not just the temperature of the start, but also the temperature of the end of this transition, the temperatures would be lower, and the temperature interval would remain as such for reverse transition. But our data and literature data demonstrates that the temperature interval of reverse transformation is much wider than for forward transformation. Therefore, we made a conclusion that this point defects influence just the origin phase of martensite transformation. And the last question was on the load. Whether we'll see further studies when we had other options of stress. Yes, we will have them, and in the work of 1993 they started the change of deformation and martensite formation in some rotation conditions, but we believe that the value of isothermal strain will be different depending on expansion, but this requires additional studies. So, are you satisfied, Tatiana? Yes, but could you explain why do you expect it to be different? Because it is defined by the shear of martensite, and as a deformation, it will just influence the volumetric shear of martensite. I'm not sure that it will influence the volumetric shear of martensite. Maybe the volume of oriented martensite that influences the deformation. And the idea is based on the fact that the reversible deformation for the same alloy will be different for expansion and for compression. Therefore, we can believe that in isothermal implementation of these defects will have certain differences in different stress regimes. Thank you. Thank you. I'm fully satisfied. Okay. Then I give the floor to Vasily Urbanik. So, dear colleagues, hello. I liked the thesis a lot. It is quite a relevant topic, and the scientific novelty is quite obvious. The results were tested on different conferences. And as for the comments that I had, the first two are dealing with are just some general recommendations. And I would like to see more structural studies on point defects in the materials that you study, and the diffusions I believe they should confirm the mechanism that you offered. It's clear that within the framework of one work, it's something that can't be done. Maybe this will be just the continuation of this work. So these comments are not quite serious, and certainly the results that the candidate for the degree received are quite valuable. Therefore, I believe that the thesis by Elena Demidova complies with all the requirements, and Ms. Demidova deserves the academic degree of the candidate of sciences in physics and mathematics. Thank you very much for the comments and for the ideas that you've given. I fully agree with all the comments. Okay. And I also want to say a few words. I've provided my review. So I say that I liked the work a lot. I like the literature review, and as Tatiana mentioned, the work is very well structured. And I can just repeat what my colleagues have already mentioned, and I can read out the formal comments. Some of them were already mentioned, and Elena explained everything to me already. In modeling the shear of definition of martensite phase, you use different equations for the parameters of the model, depending on the temperature, whether it was higher or lower than the temperature of forward transition. However, in the modeling of change of reverse deformation, you use the parameters that are independent from the temperature choice. And does it mean that the holding under stress of kinetic isothermal transition, these parameters are the same? And it's unclear what are the ideas according to which you choose the activation energy values in the modeling of microstructural model. And in order to calculate the reverse deformation, you calculate the shear of martensite in isothermal conditions, and you don't demonstrate the dependencies of shear of martensite on time, and it's unclear whether it complies with the dependencies of the strain from time. But still, I believe that the thesis is certainly satisfied all the requirements. It's very well written. And the new results are not questioned. Therefore, I believe that it certainly meets the requirements of the order on the procedure of granting academic degree, and I believe that Ms. Demidova deserves the academic degree of the candidate of sciences in physics and mathematics. Thank you very much for the review and for the comments. As for the first question, whether kinetics is changing at different temperatures, no, I believe not, because in our work we observed the isothermal change of strain. There were some isothermal effects under stress when we used the temperature, when we were working within the temperature regime. And there was just one parameter that changed when the temperature was lower than the chosen range. And also the calculated and experimental dependencies of deformation on temperature and on holding time that we received at temperature that is 6 degrees lower than the start of transformation temperature. They were very close and similar, and in these conditions our calculations were close to experimental data. And as for the physical processes, we did not compare our activation energy with these different processes, with certain physical processes. And as for reverse deformation, it is directly proportional to the volumetric shear of martensite, and these dependencies were similar to the ones received by a structural analytical model. Okay, thank you. Any other questions to our candidate for the degree? Is everyone satisfied with the answers? Yes, I believe so. Okay. Is anyone willing to speak out? So, okay. We've already discussed everything, I believe. And there are no questions submitted online. Well then, I give the floor to the thesis supervisor. So, Elena has been working in our group since third year, and if a person continues the PhD course, the person continues the scientific topic that he developed during other works. And Elena is an exception here because she fully changed the topic when she joined the PhD course, and this is connected with the fact that in 2016 we saw a lot of new information on the isothermal martensite transformations in certain alloys in isothermal conditions, and at that point it was considered exotic, and sometimes it was even criticized because for 15 years we got used to thermal conditions in titanium and nickel alloys. Therefore, she had such an interesting task to consider the transformations in isothermal conditions, and she should have found the strains and the effects of such transitions, and Elena is a kind of pioneer in such developments, and certainly her work is connected with mechanics more, but in order to modify the existing models, in order to try to describe the deformation changes, we need to understand the processes first of all. Therefore, she had to improve her knowledge in physics and physical material science in order to understand the processes that happen in phase transitions. Therefore, she used this knowledge in modeling. And Elena has worked quite successfully, and she carried out a range of experiments, and everything looks quite nice during presentation, but these 3 or 4 points, they require 3 or 4 months of time. And the same is true for modeling, because it was mentioned shortly that new parameters were introduced and they were selected according to experimental data, but this procedure required several months as well, so that everything would be adequate and would comply with other data. So she is quite a qualified researcher, and I'm sure that she deserves the academic degree of the candidate of sciences. Distinguished colleagues, is anyone willing to give his or her point of view on the work? Are there any questions? Is anyone willing to give their opinion? Dear colleagues who are working remotely? No. Actually, we discussed everything, and we can organize a short discussion to discuss the results of the defense, but I believe we didn't have any contradictions, therefore I believe that there's no need for that. We can skip that point. Okay, then I raise a question on the award of the academic degree until Elena, and we're going to have an open balloting right now. And let me remind you that the decision of the dissertation board on conferring the academic degree is positive, provided more than 50% of the board members voted in favor. So, Yulia, what's your point of view? I vote for the award of the academic degree. Victor, what about you? Certainly I vote for. Tatiana? Certainly, I also vote for the award of the academic degree. Vasily, what about you? I vote for the award of the academic degree as well, and I vote for the award of the academic degree as well. Thus, distinguished colleagues, I would like to announce that out of the 5 members of the board, everyone voted for the award of the academic degree. No one voted against that, and the decision on the award of the academic degree to Elena is made. Distinguished colleagues, due to the fact that our session is held online, I would like to ask if the members of the board or the candidate for the degree or anyone else present have any questions on the procedure. Yes, certainly the finalizing remarks. Yes, thank you very much. I would like to thank all the members of the board for taking part in the defense and for the time that you spent on studying this work. And I would also like to express my gratitude to my scientific supervisors, Natalia and Sergei Pavlovich, for the support and for help during this process. And I would like to thank my parents and my friends for their moral support. And I would like to thank the dissertation board support. Thank you very much. I therefore close our session, and I would like to thank everyone for taking part in it. And kindly turn off the broadcast. And we can